I'd like to thanks to Professor and the other guys to give a chance to give a talk here. And the title of this talk is Multiple Self-Avoiding Polygons and the Step Matrix Algorithm. And this is joint work with Kyungpo Hong, my student. And here's some backgrounds of the lattice polygon statistics. And actually, I studied this object just few months, so I'm not a. Just give some overview. So here we'll talk about the some self-avoiding works and polygons on the square lattice. It's just planar square lattice. So G2 means just planar square lattice, and we're going to think about two models. One is self-avoiding work, and the other one is self-avoiding polygons. And so self-avoiding work is just an arc on the lattice, and they must start at the origin. And for the self-avoiding polygons, we don't need to start at the origin, but if you can get one from the other by translation, then we'll think about they are same. So today we'll think about the self-avoiding works of length n starting at the origin. That is called, the number of self-avoiding works is called Cn, and the other one is the number of self-avoiding polygons of length n up to translation, and that is called Pn. And actually, the problem about self-avoiding works and polygons, the definition is very simple, but it's extremely difficult to solve, to find the exact number of Cn and Pn.
Excuse me. So you don't, for the self-avoiding works, you do not factor out by any rotation or reflection or anything?
Oh, they're all different.
They're all different.
Yeah.
Uh-huh.
Yeah. It's totally different.
But there you factor out by translation.
Just for translation, not orientation.
Okay.
So all they are different. So you're gonna try to find out the total number of C.
Okay.
So that was introduced by two famous theoretical chemists, Orr and Florey, in 1940s as a model of polymer in dilute solution. But I don't want to talk about that kind of things. And after that problem posed, it became very interesting combinatorial models. And many attempts to count the number of works and polygons have led to the development of many algorithms with widespread application to the applied math, chemistry, biology, and even industry. Actually, during the 70 years, we have huge amount of numerical informations and substantial amount of exact information. The exact means, they are right, but not proved yet. So they believe that is true. And for the mathematically proved result, they are very small results are proved. And here's several major breakthroughs. The first one is 1950s harmlessly proved that the existence of limit of Cn to the 1/nth power, and also he proved that the existence of limit of Pn to the 1/nth power, they are called connective constant. But he showed that their existence, but nobody knows what's the exact number of mu. Because Cn and Pn, they grow exponentially. And until now, so many mathematicians, they are trying to find the exact number of Cn also and mu, but still they found just Cn for just 79. And for mu, the best estimate is something like that. And also, a few years ago, Demi Lee, Shopping, and Simonov, they found the exact number of mu, but not on the square lattice. They use hexagonal lattice. That's a little bit easier than square lattice. And that's the first result proved mathematically. And also, for general things, they are conjectured like Pn is just like some constant times of mu to the nth power and times n to the lambdath power, and they'll try to find the exact number of mu and lambda.
So what do you mean by even n?
For the self-forwarding works, we don't need to the condition of n is equal n is even, but for the polygon, actually we need even condition, right? Because
Otherwise it's zero.
Yeah. And today I'll talk about not self-avoiding polygons. I'm going to talk about multiple self-avoiding polygons, and also we're going to talk about, we're going to put the model on the confined square lattice, not infinite lattice. So just think about a rectangle in the square lattice. So they have m rows and n columns. So that is called GMN. And in the confined region, we'll think about the multiple self-forwarding works. And we don't need to think about the translation. They are all different. So here's a GMN. There's one example of multiple self-forwarding polygons, and that has two components. And small pmn is the total number of multiple self-forwarding polygons in GMN. And pmnd is especially, we'll think about the polygons with length n, length d. And large pmnt is a length generating function. So here, if I put the 1 on the t, then we get small pmn. So here's the main theorem. So we found some algorithm to find the generating function directly, but it's quite it's a heavy matrix. So first start at this x1 and o1, that's 2 by 2 matrix. And we get some xm and om by using these recurrence relations. So each time the size of matrix is bigger and bigger, because the size is bigger by 2 times, right? And then finally we get the matrix xm and multiply by n times, and then just take a 1 entry of that and delete n minus 1. Then that's the generating function. So for example, if I use that algorithm, then if I just find the 3 by 3 rectangular lattice, and if you use that algorithm, then you get this equation. And also we can find that polynomial directly from the graph, from the figure. So we have 3 by 3 lattice, and if you try to find all the polygons here, then the first we can find the 4 polygons with length 4, and I missed it. We don't need this one. So we find another 4 polygons of length 6, and lastly we find 5 polygons of length 8. So if you use that algorithm, then we have same polynomials, but if you use this figure, we get the same result. And also, if you put 1 to the t, then we get 13. So 3 by 3 lattice, totally we have 13 multiple self-avoiding polygons. And actually, that either comes from the non-mosaics and then that's from the knot theory. And actually, the non-mosaic, Lomonaco and Kaufman introduced non-mosaic system to give a precise and workable definition of quantum knots. And in the non-mosaic system, actually we use 11 kinds of mosaic tiles like that. And if I use this mosaic tiles, we define some MM mosaics. MM mosaic is M by N matrix, and each entry is one of these mosaic tiles. So here's one example of MM mosaics. And this has no meaning, but if you put some another restriction called suitably connected, that means the end point of the arcs, they are all matched up. Then we get some nice diagram of one knot. So if you put the condition, then we get knot MM mosaics. And in the theory of non-mosaics, one of the big problems is like how many non-mosaics are there from the fixed size. So here dmn is the total number of knot MM mosaics. Actually, that has easy upper bound 11 to the mn because each tile has 11 choices, right?
So you don't care number of components in the knots?
Oh, we don't think about the number of components. Yeah. So here's some known result proved by our team. The first one is like dmn has some upper bound, but we have to think about only this number. That's the biggest power. So we reduce the 11 to the 4.4. And the second result is to find the exact number of dmn. So it's quadratically exponentially increased. So it's quite difficult to find the exact number. So even though we want to try to find d6 and 6, it's almost, how big? I'm not sure. It's 100 trillion something? Yeah. And also, we get some matrix algorithm. So we found the dmn, the exact number of dmn by using these recurrence relations. That's the original version of state matrix algorithm. So I don't want to prove that, but just think about that's a little bit similar to our main theorem, right? So during 3 years, we wrote several papers about non-mosaics. So, and this paper contains that old version of state matrix algorithm. And also we apply that algorithm to the toroidal case or some graph mosaic. So now I'll explain how to apply this state matrix algorithm to the self-avoiding polygon model. So here's the 3 steps of state matrix algorithm. The first step is conversion to planar mosaics. So at this step, we're gonna move the polygon from the planar lattice to the mosaic system. And the second step, we'll find the recurrence formula. We're gonna explain the definition of state matrix and try to find the recursion formula. And the step 3, we're going to analyze in state matrix to find the exact number. So for the first step, it's very simple. So the yellow one, so that's a rectangular lattice, right? So there's multiple polygons inside the lattice. But if you think about the pink one, that's the mosaic system. So the polygon, they must lie on the lattice, but in the mosaic system, then we're going to use only 7 types of mosaic tiles. Then we can explain everything, right? So in this case, we don't need to give any crosses on the mosaic. So we're gonna delete 4 mosaics from the original mosaic, 11 mosaic tiles. So we will use only 7 mosaic tiles. So in the step 2, state matrix recursion formula. So the large S PQ is the set of all suitably connected PQ mosaics. So here's one example of suitably connected 4-3 mosaics. So it has 4 rows and 3 columns and some arcs inside. And then I'll give some notations. So for each mosaic tiles, and look at the edges here, and this one has, this point is the end of this arc, right? This is called connection point. So if this edge has connection points, we note O, and if it doesn't have, then we note X. And also for this 4-3 mosaics, so we're gonna define L state and R, T, and B states. L state means the left state. That means the presence of the connection point from the bottom to the top. So in this case, OXXO. So the left state of S43, this mosaic OXXO. And this one for the right state. So OXO. And for the top state, from the right to the left. So OXX. And for the bottom, OX. So you get OX. That's the state of the PQ mosaics. And also, for the left state, they have 4 edges, and each edge has 2 choices. So total, they have 2 to the 4th power choices, right? So XXX or XXXO. So we're gonna we'll give an order of these choices and these states. So dictionary order will give. And also, I will define the state polynomial with respect to the length for given L, R, T, and B states. So in this case, all 4 states are fixed, right? So in this case, the left state is like XOO, and bottom state is like XXX. And after the 4 states are fixed, then the state polynomial we can define like that. So in this case, we have all 8 choices of polygons, not polygons here, but 8 choices of 3 mosaics. And the state polynomial is like that. So here we have 1 choice of the mosaics with length 4, and 2 choices of mosaics of length 6, and there are the 5 choices of mosaics length 8. So that's the state polynomial.
And you don't care whether they are connected or not?
We don't care. Yeah.
It has to be suitably
yeah.
connected and important.
Oh, suitably connected inside. We don't think about the boundary. So it must be suitably connected inside. And now we'll define some kind of state matrix. So the first one is column state matrix. So we have 2 kinds of column state matrix. One is OP and the other one is XP. So from the whole mosaics, we'll just think about just one column, any one column. So maybe this column or that column. So the P means the length of this column. So this one means just X3, and this one means O4. And X means the bottom state. O means the bottom state is O. And the top state is always X. And so the XP is the 2P times 2P matrix. And each entry is the state polynomial for given I's L state and J's R state, and X top state and X bottom state. So actually for the left state, if the length of this column is P, so they have two to the P's choices. So we give some order, then this is the order of the states, 2P or 2P states. So this I indicates the left state, and this J indicates the right state. So if the first row of this matrix then implies just X, 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 and the last row of this state is like O, O, O. So we have a huge matrix. So here's an example of X2. So each row indicates the state of the left state. So the first one is XX, XO, OX, and OO. And also the column. The column indicates the right state. So we have another 4 choices here. And just think about one entry here. That means the left state is like XO and the right state is OX. So we start at the bottom. So left state is like XO and right state is OX. So the top state must be X, and we want to find X2. That means the bottom state must be X, and left state is like XO, and right state is OX. Then there's only one choice. And this one has length 2, so we put T squared. If you find O2, then we have to put O here. Then the arc must start here, right? So now we'll try to find the exact column state matrix. So the X1 is the easiest one, right? So for X1, we have just one mosaic tile. So X1 means the all top state is X and all bottom states also X. And also the 1, 1 entry means the left state X and right state X. So they have only one choice. So we put just 1 because the length is 0, but they have one choice. And for the second one, the 1, 2 entry, that means left state X and right state O. But we cannot put the mosaic tiles there, right? Because each mosaic tile, they must have 0 or 2 connection points. So it does not happen. So the number of things is 0. So state polynomial is 0. And for the case of this one, the top state must be X and the bottom state must be O. And for this one, left state must be X and right state must be O. So they have only one choice. And this one has length 1, so we put T here, right? And now we'll try to find the recurrence relation here. So for the case of the column of length k plus 1, so here's the k plus 1 mosaic tiles in one column. And then here we'll try to find x k plus 1. Then the bottom state must be x here. And O k plus 1, the bottom state must be O here. And look at this one. There must be start X here, right? Because the upper half of the matrix, each row start X here, right? And the bottom half, they start O here, right? Because we use dictionary order. So this X means this one must be X. And the right side of the half matrix is start O, so it must be O. So if you put the X, and O, then the arc must be like that. So this upper part, only think about this upper part, this K1 mosaic, and it has O bottom stage. So we have to put OK here. And we add one arc here, so we have to multiply by T. So by this idea, we get these recurrence relations. And also, the last one, if we have 3 connection points, then it does not happen. So we have to zero matrix here.
And can you explain the T times OK?
Yeah.
So you multiply T for every entry? Or?
Yeah, every entry, because this OK indicates all the case of this one, which has just O bottom state, right? And all the case, we just add just one arc here, right? So each entry we have to multiply by T.
So OK is for one column?
Yeah, one column. Yeah. And every entry in the OK, they have connection points here, right? And we have to add this mosaic tiles for each one. So we have to multiply by T. And now we're going to define another state matrix XMP. So here, the column matrix, I mean, the total and the maximum length is M, right? The maximum length is M. And actually, eventually we have to find the multiple self-avoiding polygons on the mosaic, and they must not have connection points here. So we have some boundary conditions. So the top state and bottom state must be X, right? So we don't want to use OM, just OX. No, XM here. So if you find just the state matrix for column state matrix for just one column, then we'll add up. So the XMP means it has M rows and P columns. And this matrix must have the size 2m times 2m, because they have 2m choice of states on the left and on the right. And each entry indicates the state polynomial for given I's L states and J's R state. And the difference is the top state and bottom state must be X. So here's the idea to get the attached to mosaics. So here we have M rows and K columns, and we have another column here. So if you want to add up, then we need suitably connected. So the R states, right states of this matrix and the left state of this matrix must be the same, right? Then we can add up like that. So that's the state matrix for this one, and that's the state matrix for this one. So if you wanna attach it, then actually look at these equations. So when you attach it, I mean, this one has S state and this one has S state. Then after we multiply it, then this count all of things, right? Because I mean, this X, I, S, K indicates the state polynomial for the I's L state and S right state. And this I, S, J indicates the state polynomial for S, L state and J, R state. Then if you multiply these two entries, that indicates the state polynomial for the I's L state and J's R state with one condition. This line must have S state. But S state, I mean, this state has 2 to the n choices, right? So if we add up from 1 to the 2 to n, then we find all the possible states here, right? Then that's the real X, I, J, K plus 1, right? Because we count all of the choices. So this equation just means this multiplication of two matrices. So eventually we get the total. The matrix for total size is like just xn to the nth power. So this matrix indicates we have m by n mosaics. Then this matrix indicates the all top states is xxxx and all the bottom states xxxx, and the left states they have, and each entry has the i's left state and j's right state. So finally we analyze the state matrix. So this matrix is also 2m times 2m matrix, and each entry is a state polynomial for the i's L states and j's R states, and top and bottom they are we call trivial states. So the left boundary, it possibly have some connection points, and on the right side they possibly have some connection points, but we don't need that because the boundary does not have connection points. That means we have to choose only trivial state here and also trivial state here. That means the trivial state here means the first row, and the trivial state for this one means first column. So we'll just pick one entry of this total matrix. That means the one entry of this matrix has no connection points on the boundary. And also the number of, this state polynomial contains the trivial one. That means no graphs inside. But we don't want to do that. We don't want the no graph inside. So we have to delete by 1 here. So that's the total number of multiple self-avoiding polygons in the m times n matrix. And actually, they have lots of applications. And during the 70 years, lots of mathematicians, they changed the model. So sometimes they use multiple self-avoiding polygons, and also you can apply to the multiple self-avoiding works and polygons. And works, that means there's some arcs on the lattice, and polygon is a circle on the lattice, right? So if you want to use the arcs inside, then we just put these 4 mosaics. So they allow to stop at some point. And also you can apply this idea to the multiple self-avoiding graphs. That means some vertex has valence 3 or 4. So we just add this mosaic tiles on the calculation. Or maybe you can apply to the periodic multiple self-avoiding polygons. The periodic means we can use here. The periodic means on the infinite lattice we can move the exactly same mosaics, right? So we need only one condition: the left state and the right state are equal. Then we can move to the horizontally, right? And also we can apply the top and bottom side equal, then we can move up and down. So we can change the boundary condition, then we can apply that. And also the last of mathematicians, they try to find the Cn and Pn for square matrix, or sometimes triangular lattice and sometimes hexagonal lattice, because in the planar lattice only 3 regular lattice: triangular, hexagonal, or square. And maybe you can apply it to the hexagonal or triangular in the first step. And here we have one good example for this case: multiple self-avoiding polygons in the confined hexagonal lattice. So we can apply the step matrix algorithm. Then we get these recurrence relations. Actually, the original recurrence relation is quite difficult to solve the exact answer by solving the recurrence relations. But for this case, we don't have zero matrix here, so it's quite easy to solve the problem directly. Then we get this number. We can solve this recurrence relation directly, so we get this number. And actually, that's the first exact counting ever. I mean, during the 7 years, nobody found the exact number of the polygons for some models or some space in some space. But that's the first example.